Good day, everybody. Welcome back to Calculus. This is the lesson that would have been done on March 25th. It is over section 5.2 from the textbook involving finding volumes. So we're about to go three-dimensional on this kind of stuff, which is kind of cool. Let's see, there was a lot of issues I saw in the first lesson I did. Number one, I should not be relying on that whiteboard because drawing with that pen is unreliable, and all this, the visual is very important. So from now on, the rest of this entire unit, I will be doing, the examples are done in the PowerPoint. They're all pretty with nice art. I also need to remember I am teaching backwards still, so things like that. So improvements over the last one, and the rest should be fine from here, and let's go and get started. Okay, so first things first, warm up today. Find the area described in each problem and sketch rectangles and the graph to indicate how you accept the integral. So practice of finding the area between two curves from section 1 of this chapter. Number 1, the area bounded between f(x) squared of x and x squared. And number 2, the area bounded by the curves of e to the x and of 1 minus x squared. So let's take a look at that. Number 1, between square root of x and x squared. So here's their graphs, and you can tell that the red one is the y equals x squared. Similarly, the blue one is the y equals square root of x1. So I'm going to do this one two different ways to kind of get you comfortable with doing vertical strips. Remember, we're doing vertical ones. We add them all up with respect to x, or you could do it with horizontal strips and add them all up with respect to y. So I'm going to show you both ways. Let's do it the first way with respect to x. So method number 1. If you're doing with respect to x, then everything's dx. That kind of sets your widths to be infinitely small dx and the height. So this sets it up to be vertical strips right here. And whenever you're doing a vertical strip, the height is the y on the top minus the y on the bottom. And the width is, of course, dx. So that's the concept right there. If you look at this, if you were to set up some strip, say from the top of the blue down to the red, well, what's the height of that thing? It's the y on the top minus the y on the bottom. On the top, the curve is y is x squared. Excuse me, square root of x for the blue one. So the top one is square root of x for the y coordinate. And down below, the y below there, well, y is x squared on that graph. So the height would be this y up from the blue minus the y of the red, which is the square root of x minus x squared. And you can see that right here in the work. So once you've got that set up, that's the height. The width is dx. Height times width is area. So you got a little tiny chunk of area. And then all you got to do is integrate it. So once you got the dA set up, a little chunk of area for one of those little strips, you just add them all up, and it's really easy after that. You just got to remember your limits. We're doing this with respect to x. So x starts over on the left where they intersect at x equals 0, and it goes all the way over to here, x equals 1. So this entire shaded region in between the two curves, bounded between them. So x goes from 0 to 1, and you set the integral, and you do it, and you would have got 1/3. Had you gone the other way, you would have done horizontal strips. Now, horizontal strips, if we were going to do it that way, it'd be the kind of something like this, like my cursor showing right here. And those strips, the height would be dy, and the width will be the x on the right minus the x on the left. So what is the x over on the right? Well, the x on the right would be the x coordinate of this red curve. Well, the red curve is y equals x squared. So that means x is the square root of y. Notice that we dropped the plus or minus because if x was plus or minus square root of y, well, one would mean x is over on the right side of the plane, Cartesian plane, for x being positive square root of y. And if x was negative square root of y, I mean, we on the left side of the Cartesian plane because that's where x's are negative. However, in this context, you're dealing with things in quadrant 1, so x is positive, so you want x to be the positive square root of y in this case. But regardless, for the strip you're setting up, the x on the right would be the square root of y, because that's what x is there. And over here, the x on the left would be the x, whatever x is for the blue curve. Now, for the blue curve, y was square root of x. So squaring both sides, that means would be x would be y squared. So the x coordinate over on the left is just y squared. So the x on the right is square root of y. The x on the left is y squared. So the width would be x on the right minus x on the left, which is y squared minus, or excuse me, square root of y on the right minus y squared on the left. And if you go set that up with method 2, you see the dA is just that little tiny width there, x on the right minus x on the left, times the height, which is dy, and that gives you a little chunk of area. And you integrate them, and it turns out in this case, y also goes from 0 to 1, because down here, this region first starts down here where y is 0. It climbs up to right up here where y is 1. So that integral would be from 0 to 1, which actually coincidentally turns out to be the same integral as the one above it. It's a dummy variable, and that also turns out to be 1/3. Now, not always are they going to look the same. That's it. If you weren't sure what the limits would be, you could figure out where these two graphs intersect. Now, on the top right, I have a bunch of algebra to show you where that would occur at. Some of them are common sense, some aren't. If you have two things that are going to intersect at some random spot, like say you have, oh, where does e to the x intersect 1 minus x? Well, you can't algebraically solve that. So try to algebraically figure out where they intersect. If it seems impossible, it probably is. And you can just use your calculator's second intersect feature to figure out where they cross at a good decimal approximation, see what happens. All right, now problem number 2 today, we were trying to find, if you go back, the area bounded between the curves of e to the x and 1 minus x squared. So looking at their graphs, the red graph is the graph of y equals 1 minus x squared. And the blue graph is the graph of y equals e to the x. So let's see what you can do here. Let's do it both ways again, just to practice both. So you're going to need expressions for y as a function of x, and you're also going to eventually need expressions for x being a function of y. If you look at their graphs and where they intersect, they're not pretty. You know, trying to figure out where e to the x crosses 1 minus x squared, like I just alluded to, there's no algebraic way to do that. So just use your calculator's second intersect features, and the intersections are given at the top there. One of them's at 0, 1, the other one's at negative 0.714, 4.489. So that's where they're going to intersect. Now, let's say you're doing things with respect to x. Let's just go ahead and jump right in. Method 1, if you were doing this with respect to x, that would mean that all your things are dx's. That means the width is dx and the height is going to be something. So it's going to be vertical strips like that. Again, what's the concept? Well, it's the area of that strip. The area is the height, which is the y on the top minus the y on the bottom, times the width, which is dx. So that's the concept. A little chunk of area, dA, is the y on the top minus y on the bottom times dx. If you were setting up this little tiny rectangle in between these two things, you would see that the y on the top is the y value of the red curve. Y is 1 minus x squared for the red curve, so the top is at whatever 1 minus x squared is. The y on the bottom is the y value of the blue curve, and it says that y is e to the x, so the y spot on the bottom would be e to the x. So y top 1 minus y bottom would be 1 minus x squared minus e to the x. That represents the height. They reach dx thick, so times dx, then I'll give you that expression for a little chunk of area at some arbitrary x. Then, of course, you just integrate them all from x being, whatever x is on the start to whatever x is at the end. It turns out that x starts at that weird number, negative 0.714-ish, and goes all the way to over to 0. So you put that in the integral, and you get out about 0.08, something like that. And you're not going to get an exact answer on this. Well, yeah, I mean, you can't, because the intersection itself is a decimal. So even if you did the calc and plugged in, you can still get a decimal. On ones like this, where you're going to get a decimal anyway, and there's probably no algebraic way to figure things out, or if there's no calculus way to figure out the integral, you are welcome to use your calculator's, integration function. You don't have to do them all by hand if it's too cumbersome. So please keep that in mind. Now, for this particular figure, we didn't have to go do dx's, little things this way and vertical strips. We could have gone the other way. We could have done things that are height of dy and a width of like this and add them all up in terms of y. So method number 2 is we're going to do that. And in this case, you'd be setting up horizontal strips, so something across like this. And what's that little area going to be? Well, it's the width, which is the x on the right, minus the x on the left, times the thickness, which is dy. Well, let's talk about these. So to get the x on the left and the x on the right, you're going to have to write these functions in terms of x equals something, in terms of y, x equals something with y, f of y. So if you look at the blue curve, it's pretty straightforward to solve for x. If y is e to the x, then x is natural log of y. The red curve, though, you got to be careful, because if you go solve for x, technically x is plus or minus the square root of 1 minus y. But again, context. Where is this intersection? Where is this region you're trying to integrate? Well, it's over here on the left side of the plane. On the left side of the plane, x's are negative. So which one should you choose? The x is plus square root of 1 minus y, or x is negative square root of 1 minus y? Well, in this case, since x's are negative, you want to choose x is negative square root of 1 minus y. So what's the width of this thing? Well, it's the x on the right, the x on the blue curve, which is natural log of y, minus the x on the left, which is negative square root of 1 minus y. So if you plug that all in, the x on the right is natural log of y, the x on the left is negative square root of 1 minus y. You subtract them, x on the right minus x on the left, to get the total width of that thing. Its height is, of course, dy, times dy, and that gives you a little chunk of area. It gives you the area, that little sliver, that little slice. And of course, you're going to integrate that, but now you're doing things with respect to y. So where do they intersect? What's the lowest y value they're at? Whatever the y coordinate is of this intersection over here, which was 0.48. Then all the y's go all the way up to this top intersection right here, which is at y equals 1. So those are your limits of integration. You plug them in, let your calculator do it, and you get the same thing, as you should, because you're finding the area between these two curves. It shouldn't matter if you do vertical strips or horizontal strips. Either way, you should be getting about 0.08. And that's your answer for your warm-up. Learning goals today, we are going to go 3D. We are going to start finding methods to find volumes of various different methods. So you could have slices of things, and apple slices. We're going to take functions, we're going to spin them around some kind of axis, and we're going to generate volumes that way. So it's kind of cool. There's 3 methods today. One's called slicing, the other's discs, and the other's washers. Discs is a special case of washers. So really, I'm going to harp on slicing and washers a lot today. And let's get right to it. Your homework, 5.1 in theory would be due today. Again, a lot of grace period. You can wait an entire week to turn it in. But here's homework 5.2. It's due on, again, should be Monday, 3:30. But technically, we're not even starting class until April 6th. So, you know, I'm going to give you a leeway on it. I have all these assignments till at least April 6th, because that's when school officially starts back up. So nothing's really due until then. But again, stay on task, because the sections are going to keep on coming. And there's no reason to just not get them over with now. You're sitting home bored, and you don't want all this stuff crammed into less time from April 6th to the end of the semester. That's not a lot of time to get all these sections done. So I'd stay on task. But 5.2, homework 5.2 is on page 397, numbers 1 through 4, 9, 21 through 26, 35 through 37, and 39 all. So, and I'll do one of those at the end of the lesson as a little gift to you, also to model things and help you through it. Okay, so last time we talked about the area between 2 curves, and here's your quick rundown of it again. Really just keep it really simple, okay? You've got to think about how high these strips are or how wide they are. That's the hard part. If you're trying to find out how high they are to the vertical strip, it's the y on the top minus the y on the bottom. The y on the top, you're going to write in terms of x's. The y on the bottom, you're going to write in terms of x's. So your height will all be in terms of x's times dx. Add them all up for all your x's, and then you will get whatever the value of that area is. Conversely, if you're going the other way, if you're doing horizontal strips like this, then what's the width of it? Well, it's the x on the right minus the x on the left. The x on the right, you want to write in terms of y, and the x on the left, you want to write in terms of y, because to get x right minus x left, they'd all be in terms of y's then. And you want in terms of y because your thickness is dy, and you're integrating with respect to y. So that's how that's going to work. And these strips, we're going to keep using these strips throughout the next few sections. So it's kind of important that you understand that basic idea, because it's going to build on itself. Okay, real quick, here's your notes for section 5.2, the crash course, if you will. There's 2 methods we're going to be talking about: slicing, excuse me, and discs and washers. Take a minute and write down these key equations. Really look at the structure of them, what's going on. Again, this will not be hard if you understand the concept and you can set up little slices and things like that. It looks really cool. We're going to make neat little figures that look like weird areas, like this top one, slicing. So where you take slices at a time of something and you know what the area is of each slice. So you can basically, if you know what the area of a slice is times the thickness of the slice, that gives you a little chunk of volume. Area times thickness is volume. So basically, you're going to add up all these little volumes as you go up, get the volume of the whole figure. Down below with discs and washers, that's what we're going to do when we take a function or a region, something, and we're going to spin it around some kind of axis of rotation, and we're going to generate some kind of volume by doing that, which is kind of cool too. So hopefully you can write those down. If you haven't yet, go ahead and do it. Pause the video. I'm going to go on. So here we go. Volume. The first method is by something called slicing. And the book defines a cylinder, which you don't think of a cylinder as you think of a cylinder as a circle on top, stuff like that. But technically, a cylinder is anything where if you take cross sections of it, it's the same kind of shape. So this rectangular prism over on the left, according to the book, it's a cylinder because if you took a slice of different parts of it, each of those slices would be a little tiny square. So here's a square, and you take a slice, each one's a square. So since it's a square going up and down, every slice is a square, that's technically a cylinder. Now the actual cylinder, like we usually talk about, if you take a slice of a cylinder, every single time you do that, what the cross-sectional area will be just a little tiny circle. So you have a circle here, a circle there, and a circle here, circle, 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 and you add them all up. But each cross-section is a circle. So that's what a cylinder is defined by this. And volume is just area times height. So for these kind of things, since they're constantly the same, thickness throughout the thing, the volume is just whatever the area is of the base times the height. If you go down to an infinitely small level, a little chunk of volume is going to be whatever that area is times a little chunk of height right there. And that's going to be the concept. It's kind of nice to think of slicing as like a loaf of bread. You want to find the volume of a loaf of bread and you knew the area equation for each slice. Well, you could find the area, the volume of every single slice, because let's say your bread is lined up this way along the x-axis and you take a little slice of it and here's your piece of bread. Well, if you know the area of this piece of bread and you know the thickness of it, which is like dx, well, the area of that thing times its thickness, dx, would be that thing's little bit of volume. If I know the volume of this slice plus the volume of that slice plus the volume of that slice and integrate them all up, I will get the entire volume for this thing, which is essentially what it's driving at right here. So right down here in this box is probably the fundamental thing. If you take areas times thicknesses, so you have an area of something times its thickness, that gives you a little tiny piece of volume, dV. So dV is like a dx, whatever the area is. And if you slap some integrals on it, and that's the easy part, once you get to set up the differential dV equals a dx, the calculus is really easy after this, as I've alluded to many times. The hard part's going to be setting it up correctly in the first place. But if you integrate both sides, there's your master equation. Volume is the integral from a to b. X starts at a and x goes to b, whatever the area is of each slice times its thickness. So a dx is a volume right there. It's a little tiny chunk of volume, area times thickness, and you're going to add up all these volumes to get the total volume right there. Okay, so this is a little weird what the book does. The book does an example soon with a pyramid, and I'm going to do that in a second, but I thought maybe we take a step back and understand generally why this works for anything that comes to a tip. If you have any kind of base at all, and you add them all up and they come to a tip, you probably know the equation for that volume is 1/3 base times height. Well, now we're going to prove it. But to simplify things a little bit, let's try to do a callback to old geometry skills. So here's a theorem I found online for similar solids. If you have two similar solids with a scale factor of a to b, all it means is they're the exact same shape. Every cross section, well, actually the big cone here is the same shape as little cone. They're similar figures. One's just scaled up in size. So basically what happens is The scale factor is called A to B. So in this case, if you look at the two, just pick any dimension. It could be their heights, it could be their radiuses or something like that. This example on this slide said the radius. So if you know the ratio of the two radii, you know the radius of one of them divided by the radius of the other, that ratio will be the same throughout. All lengths, one-dimensional things got scaled up by that ratio. So if the radius got scaled down by a half, the height got scaled down by a half. So everything got scaled down by that ratio. So for example, if you had a, let's just say something really easy, a stupid, like a line that's 5 long, and you scale it all up by a factor of, 10. If it used to be 5, for example, and now it's 10, well, the scale factor is 2. Everything got 2 times longer. And that's nothing complicated. That makes sense with lengths, correct? However, with areas, and this is the main thing we need to concentrate on here, that scale factor is squared. And I want you to think of like a cube, maybe why that is. If you had a cube and it was initially 1 unit, not a cube, let's not say a cube, square. You had a square and it was 1 unit high and 1 unit wide, 1 by 1. Well, clearly that area would be 1 times 1. If you scale everything up, though, by, say, a factor of 2, that the scale means that every length gets 2 times bigger. Well, that means that the width isn't 1, now it's 2, and the height isn't 1, it's now 2. So you've doubled both the dimensions. It's 2 times bigger everywhere. Does that mean the area is twice as much? No, it doesn't, because if that top used to be 1 long and now it's 2, and it used to be 1 high and now it's 2. Well, now it's a 2 by 2, which makes an area of 4. So the old area used to be 1 when it was 1 by 1. Now the new area is 4 when it's 2 by 2. What factor did that go up by? It went up by a factor of 4. The scale factor was 2. We multiplied all the lengths by 2, but the area got scaled up by a factor of 4, 2 squared. Similarly, if you had like a little rectangle, let's say a square that was 1 by 1, well, that's an area of 1. And if you tripled everything, well, then it'd be, the scale factor is 3, but the area didn't go up by that factor. It went up by, well, let's see, this is 3 long now, this is 3 high now, so 3 times 3 is 9. It went up by a factor of 9, which is 3 squared. So the moral of the story is, if you have similar shapes, and you scale them up linearly, all their dimensions get scaled up by a steady amount. The area actually gets increased by whatever that scaling factor is squared, which is pretty darn useful. Now, you can go 3D on this too. We're not going to need that for the lesson, but if you had a cube, for example, 1 by 1 by 1, well, 1 by 1 by 1, that volume would be 1. And let's say you scale it up by 3, so every length is 3 times bigger, so now it's 3 by 3 by 3. Well, that volume would be 27, which is the scale factor 3 cubed. If you want to go crazy and do 4 dimensions or something like that, you could scale something, you could have a 4-dimensional object, and then scale everything up by a factor, and its 4-dimensional volume would get scaled up by a factor of the scale factor to the 4th power. So that's the big idea behind that. Now, why am I harping on this so much? Well, let's talk about this 1/3 base times height thing. Let's say you have any kind of, I don't know, let's say it's a kind of like a pyramid or a cone or something like that. Anything that comes to a tip with any weird base, and that base could be any shape, but it gets just scaled down as you go up to the tip at the very top. And to make things easier, I went ahead and flipped this upside down. Normally you have the base at the bottom and the tip at the top, but the calculus is a little easier if you invert that thing. So if you take a look at this picture, let's say you had some random base B at the top here. And this figure comes down to a point. So it's just like a pyramid, all the sides come up to the very top. Everything's scaled up as it goes. But if you look at this, basically as you do this, look on the side. The side is going up as a line. So since it's going up as a line, it's linear. That means that the side lengths of all these things are going up in a nice linear fashion. So what's the scale factor in this case? Well, Let's take a look. If you're at this slice right here, so pretend you took a slice out of this middle, random spot, took a slice out of that thing, and you want to know what's the area of that little slice compared to the original area of the base. Well, if you set up similar triangles kind of thing, turns out that this y value, this length right here, on this similar triangle is similar to the height of the entire figure, which is h. So if you're only y high out of h, then all the dimensions are only y divided by h as big as they are on the top. Notice down at the very corner there, at the very point, the vertex where everything meets, y is 0. Well, how big is that figure at that tip? It's none. It's all collapsed down to an area that's 0. And then when you get all the way to the top, you know, what's the y value at the top? Well, it's whatever the height is, h. And the scale factor then will be 1. So because you're at the top, so the base is, the area at the top is the area of the base. And as you go down linearly across this, all the dimensions are adjusted by this scale factor. So what's the area of that little slice right there? A of y, not the top, not the base, just that random cross-sectional we sliced out of this thing. Well, it's the same shape as the base on the top, but all the dimensions have gotten shrunk down by a factor of y over h at that spot. And as we just talked about, areas are related to the scale factor squared. So the area of that slice is whatever the area of the base is up top, but it got scaled down by a factor of y over h, so that area got scaled down by a factor of y over h squared. So that leads us to this big equation right here. This area of this little slice, whatever the base was on top, it's the same shape, but it got scaled down the area by a factor of y over h squared. Okay, so that's all the theory behind it. Now, how are you going to find the volume of this thing? Because the point is to find a volume. This section is about volume. Well, if you know what the area of that cross section is, which we just talked about, how thick is that? Well, it's dy. We're integrating with respect to y in my example. Dy thick. And area times thickness is volume. So a little chunk of volume, dv, is that cross-sectional area times the thickness, which is dy. Well, the cross-sectional area, like we just said, is the base on the top times the scale factor squared, which is y over h squared. And dy is dy. So you get the equation for dv is whatever the base is times y over h squared dy. Now slap some integrals on this, and we can add up all these little areas, this little small area, bigger area, longer area, all the way to the top, all the slices of bread. And remember, the base is a constant for this thing. It's a constant area on top. The height of this figure is a constant. So when you slap some integrals on this thing, well, where does y go from? It goes from the very bottom, which I assume is at y equals 0, all the way to the top where y is h. So our limits for integration with respect to y are from 0 up to h. And you go and simplify things, you get the integral of just y squared dy essentially when you bring in all the constants. And the integral, that's 1/3. Now we see where that 1/3 comes from in the volume equation. 1/3 y cubed, you plug in your limits from h to 0, you clean it all up, and you get that the volume of this thing is 1/3 the base, whatever the base's shape's area is on top. The base stands for the area on top, whatever weird shape it is. It could be a pyramid with a square on top. It could be a cylinder with a circle on top. It could be anything like that. But as long as they come to a tip like this, then the volume of this thing is 1/3 base times height, which is where that geometric equation comes from. So now you're starting to see where some of these equations come from, which is kind of cool. Okay, so the book officially is going to do this with, they're going to do it a little different. They're going to do it with specific numbers, and they're going to kind of scoot things over so it's not centered there, and they're going to have it going up instead of mine, which was going down like this. But we'll get through it. So here's their first example of using slicing. Normally the problems aren't this bad. Usually the problem will just say, here's the area equation. Area is this. If its area is a function of x, then you know the area at a certain x and the thickness is dx, and you just add them all up, or vice versa. Here's the area as a function of y, and the thickness is dy, so you multiply the volume and add them all up. This one's a little tricky, so I thought I'd go over it. This one says the Pyramid Arena in Memphis has a square base side, approximately 600 feet. So if you look at this figure, this side's 600 square, so this side's 600 also. The height of this figure is 320 feet, the height of it is. Find the volume of the pyramid with these measurements. Okay, well, it's just 1/3 base times height. I derived a very general equation for this, and you could just plug it into that, but let's do it the book way. So what are they doing? Well, they're first talking about the scale, like I said, the scale factor, whatever that is, whatever the dimensions go up by as you go along, that factor gets squared. So whatever happens to the sides as you go around is what's important. If you know how the sides are going up, which is linearly, and you can see that each side goes up kind of in a straight line. There's a straight line from the top down. And they all just get shorter and shorter and shorter, the side length of this pyramid as you go up. Well, let's think about this now. Look at their coordinate system. This is important too. They say in the x-axis is up. So it doesn't really matter, you don't need any other y's or z coordinates or anything like that, but x is going up. And here's how they center this thing. Now, at x equals 0, which means on the bottom, at the base, the cross-section of a square, one of the sides is 600. When you go all the way to the top of this pyramid, where x is 320 at the tip, well, how wide is this square at the top? There is no square. So at x equals 320 at the top, the length of the side of your square is 0. Now, they're going to define f of x to represent the length of the side of a square of a cross-section. So take a cross-section, you slice this pyramid at some spot. F of x represents the side of the square that results when you cross-section it. Now it's going to go up, what do we know about this? Well, that means f of 0 is 600 because f of x represents the length of the cross-section. And when you slice at 0, it's just the base. So f of 0 is the side length of the base, which is 600. F of 320 is the cross-sectional side length of the square at the very top. There is no square at the top, so it's 0. And it has to be a linear function because it's going up steadily. So here's what they're going to do. The first thing they're going to do is say, since f of 0 is 600 and f of 320 is 0, they can figure out what equation for f of x since it's a linear function. Find the slope of it. The slope is 600 minus 0, rise over run, over 0 minus 320, and that's -5/8. And you could use a point slope form or something like that to figure out that the equation for the side length at any x value is -15/8x plus 600. Okay, now remember the area of this thing, there's two ways to do it. You could say it's just the area of the base times the scale factor squared. You could do that. But since I did all this work, they know that for a cross-sectional slice, they know what the side lengths are. They know that the side length is f of x on this side and f of x on this side. So what's the area of this thing? Well, it's a square. So the area of this square is going to be whatever f of x is times f of x, so or f of x squared. And that's exactly what they do. The area is the f of x squared, the length of each side squared. The thickness of each volume is dx. So a little chunk of volume is the -15/8x plus 600 squared. That is the area of the square, the length and the width multiplied together, squared since they're the same, times the thickness, which is dx. And then you integrate them all up with respect to x. X goes from, in this figure, it goes from 0 up to the height, which is 320. You go do all that and do the rudimentary calculus, and you get 38,400,000 as your answer. Now, you should have units if there's units in these things. Note, if you go back to the original problem, they said that all these things about this were in 600 feet and 320 feet. So volume for this would be 38,400,000 feet cubed since it's a volume. And that's about it for slicing. Now, most of the problems aren't going to be that difficult. Most of them you're not going to set up some kind of, thing like this, so linear function for this and linear function for that. Most of the problem will just say, hey, here's the equation for the area. You don't need to think about it. The area of this slice is this. All you got to know is just times dx to get the volume and add them all up. So hopefully they won't be too strenuous, but if they are, we can work on it together. Okay, that's it for slicing. Now, there's two other methods. They're really the same method, but we're going to go through them one at a time. Discs and washers. Discs is a special case of washers, but you kind of want to get discs down because washers are the same kind of thing. So here's the method of discs. Suppose that you got a function greater than or equal to 0, so it just doesn't cross the axis. It's always above this. It could also be below the axis. The key thing is you don't want to, well, you could cross the axis too. there's technicalities in here. It's a continuous function. That's mostly what's important. It's nice and smooth, and there's no bumps or anything like that. Now for this particular thing, they're starting out talking about doing a region bounded by the curve and the x-axis. It's implied in these as between the curve and the x-axis. It doesn't always have to be between the x-axis, but we'll start on this. Now, if you took a function on this left, say you had some function and all the area underneath of it, between it and the x-axis, you could find that with strips, but that's not the point. The point isn't to find the area for when you're using disks. What we want to do is if we took this figure and we spun it around, the entire figure, just rotated around, it would create a volume. So you can see that if you took this figure on the left and spun it, that whole blue area, you spun it around the x-axis, you get a volume, which is called a solid of revolution. And that's what the method of disks is good for. It's good for if you take some function and spin it around some line. It doesn't even have to be the x-axis. But if you took a little tiny chunk of it and spun it around, a little tiny chunk of it, dx, a little tiny strip. If you took a strip and spun it around, that entire strip spun around, it would create a circle. So what you can see here is, here's the big concept behind it. Let's say you took this little thing on the figure on the left and you were going to spin it around the x-axis. Well, you can't spin the whole thing around at once. The whole point of calculus is to spin around a little chunk at a time. So what you would do is take a little tiny strip, just like we've been doing. So I'm drawing like a vertical strip here with my cursor right now. And we would just take that strip and rotate that strip around and get the volume of that, just that little tiny piece of strip. Well, let's think about this. So what would you get if you took a strip, a vertical line up and down, and spun it around an axis? Well, you'd create a circle. And the cross section of that circle right here, this kind of pretty one, well, what's the volume of that circle? Well, the area, the slice, if you go back to slicing for a second, well, that slice is just a circle. So its area is pi r squared. We don't want area, we want volume. What's the volume of it then? Well, it's that cross-sectional area, pi r squared, times the thickness, which is dx in this picture. And that would give you a little chunk of volume. Area times thickness is volume. So if you know the area is pi r squared and the thickness is dx, that gives you a little chunk of volume. And that's essentially what they're going on right here. So here's their equation. I like the one I have in my notes better because it's not always, the radius isn't always going to be f of x. If you're going from the function down to the x-axis, sure, that height of that little strip is going to be whatever f of x is minus 0, or just f of x. This is more general than that, but this is an equation for if you are revolving a function, y equals f of x, around just the x-axis. In general, I'd like you to think of it more as pi r squared. Think about what r is, the distance from your function to whatever you're rotating around. Pi r squared times the thickness is what we're going to do there. This is called the method of disks right here, because you're going to have little disks, and disks are just kind of circles with some thickness, and you're going to add them all up, essentially. So if you can find the equation for the volume of one of these little slices, you're going to take a slice, you're going to take a little tiny rectangle, like we did in the last section, you're going to spin it around to get an area, pi r squared, times the thickness, and that's the volume of that disk, and you're going to integrate them all up from there to there. So let's look at a specific example. Let's say they said revolve the region under the curve y equals square root of x, there it is in green on the left, on the interval 0 to 4, so they're flat saying x goes from 0 to x equals 4, about the x-axis, and find the volume of the resulting solid of revolution. Okay, well, here's this function right here, this green one, and we're going to try to revolve it around this axis, the x-axis, this little rotation thing. Well, how are we going to do that? We're not going to do the whole thing at once. We're going to take a sliver. So if you took a little sliver of this thing, well, what's the radius? What's the radius of the circle that when you spin around it's going to be? Well, it's going to be the height of the sliver. This sliver starts up here and goes down to the x-axis. So right here, this little slice, just like we've been doing, so what's the area of that rectangle? Well, what's the height of it at least? the height of this rectangle is going to be whatever the y is on the top minus whatever y is on the bottom. And the thickness of it's going to be dx. So you want to write everything in terms of x's. Well, what is the y on the top? The y on the top is whatever the y coordinate is up here, which is square root of x, right? And minus whatever the y coordinate is down here, which is 0. So basically that height's just going to be whatever the function is, which is square root of x. The height, think about that. When you have a strip this high and you spin it around, that height will represent the radius of the circle you make. So the radius we're going to have is going to be square root of x. When you spin it around, that area will be pi r squared. So pi r squared is going to be pi times the square root of x squared. And that gives you the area of that particular circle times its thickness, which is going to be dx in this case. Will give you a little chunk of volume, and then you add them all up. So here's how I finish it up. The volume is pi r squared. A little chunk of volume is pi r squared times the thickness. So like I just said, the radius is going to be square root of x when you spin it around and make a circle. The circle of radius square root of x. The thickness of this particular circle is going to be dx. So you multiply the area times the thickness to get the little tiny chunk of volume, which is pi times the square root of x squared dx. What are the limits of this? If that's just a little chunk of volume, then you need to add up all these volumes as you go through all these little slices. Well, let's see here. X, according to this figure, x starts at 0 and goes to 4, and that's what they flat out tells you from 0 to 4, so the limits are from 0 to 4. After that's pretty trivial. You do the basic calculus, you would have got the volume of this figure being 8 pi, units cubed. You don't need to write units cubed. If there's no units given, just write 8 pi because it's unitless. So there you go on that. Of course, you don't need to do this all with vertical circles that are dx thick. No, you could go the other way. You could have horizontal circles that are dy thick and add up all the circles going up that way. So it's a very much the same concept if you're going the other direction. Now let's set up though. Let's just think about it conceptually. What if I was doing this region on the left and spinning around the y-axis? Well, this time I would take a strip, a horizontal strip, and the radius would be whatever the length of that strip is. And when it's spun around, that'll be my radius. The area will be pi r squared times the thickness, which in this case is dy. Well, how do you find the width of this strip right here? Well, it's the x on the right minus the x on the left. In this case, if you're going around the y-axis, x on the left is just whatever g of y is. And over on the left, the x value is 0. So the entire length of this strip is just whatever the x value is on the right, which is g of y. So the radius of this thing, when you spin it around, is just whatever g of y is. So it's pi times g of y squared, because that's the radius squared, times the thickness, which is dy. That gives you the volume of that disk. And then you add up all the disk's volume from whatever, y starts at to whatever y ends at, c to d. Usually they do a to b for x's and c to d for y's. It's just a convention. Then you integrate all of them and you're done. So that's good. And I think this slide, the main thing it says is don't make the mistake of simply looking where you plug in where. This is very much geometric. You want to figure out what the radius is as a concept. You want to figure out what the thickness is, either dx or dy. As a concept, you want to understand that the volume of these disks is the area of the disk times the thickness. What's the area of a disk? It's a circle. It's pi r squared. And what's the r come from? It comes from the distance from your function to the axis of rotation. That's your radius that gets spun around. So you want to think about thinking through things through like that. Don't just try, oh, here's an equation, I plug this in here. It's not going to work. Pi r squared times the thickness. That's the concept. Okay, so that's disks. Now, disks are a special case of washers. What's the difference between a washer and a disk? A disk is a circle entirely filled in. A washer is a circle with a circle taken out of it. So what's the difference here? Well, it's certainly disks, but essentially we're going to be this is good for some kind of thing that you're trying to rotate a function around, but there's a hole in it. you don't want some of the inside to be rotated around. You just want region to be spun around, but there's some inside you don't want to spin around. So here's kind of an example. Let's say you had this picture right here. It's kind of hard what the original function was, but the original function was some kind of parabola like this. So what I'm sweeping out with my mouse right here is the original function. And you want to take the volume of this by finding the region bounded between the y-axis right here, the line y equals 1 right here, and this. So if you look at this, it's kind of like this quarter circle-ish kind of figure right here. If you took that figure and you wanted to rotate it around the x-axis, well, there's a problem, because notice that this area here in darker green would be spun around also, and you don't want that inside to be spun around. Basically, the cross-section area of this would be the top part spun around minus the bottom part spun around. So you see it makes a little washer right here. It's got a hole in it, hence why it's called washers. You also want to keep this one in mind for when you're spinning around lines other than the x-axis or the y-axis. Now, you can do that with discs. You don't have to use washers. Again, this is why I keep harping on the concept. It's pi r squared. So what r is will depend on the situation. But as long as you remember, hey, I'm doing pi r squared times the thickness, you'll be all right. So here's that one worked out a little bit. Let's say r is the region bounded by the graphs of y equals 1/4 x squared. So it was some kind of parabola in that figure. X equals 0. X equals 0 is the y-axis, and y equals 1. So just like I was alluding to, this region right here, you want to spin it around. Now, if you took the outside, what's the outer radius here? Well, pretend that for a second you were spinning this entire thing around, including this white part from 0 to 2 that was filled in. This entire box here, this entire square, rectangle technically, is filled in, and you want to spin around the axis x equals 2. Well, how would you do that? Well, what's the radius that you're doing? It's pi r squared times the thickness. Well, if you were setting up a strip right here, from the top to the bottom, it'd be the y on the top minus the y on the bottom, which across the entire way would be 1 minus 0, 1 minus 0, 1 minus 0. And that radius would always be 1. And so what's the volume? It's pi r squared, which is pi times 1 squared, or pi, times the thickness. Now, if I was doing a vertical one like this from the x-axis all the way up, the thickness would be dx. So if I was taking the entire rectangle here, from x goes from 0 to 2, and y goes from 0 to 1, the whole thing, and spinning around, then I'd get pi times 1 squared times the thickness dx. I'd integrate x from 0 to 2, and I'd be done. But note the problem. We don't want to spin the whole thing around. That'd be too much. We don't want to spin this white part around. Well, it's an easy fix, actually. If you can spin the whole thing around, including that gap, well, how are you going to account for that gap? You're going to subtract the volume of just the gap spun around. So if you just took this white part and spun around, you get another volume. So that's what washers are. Washers are when there's some inside part that you don't want spun around. So what do? You spin the whole thing around, including that inside little part, and then you subtract off what you get when you just spin that inside part around. So at first you include the inside part with your outer radius, and you subtract off that little part, the inner radius, when you're done. Now you can set this all up at once. You don't have to do it as two separate integrals. You can set up as the following right here. So what do? Well, it's pi r squared. Essentially, what you're doing is you're going to find the volume of this thing all the way to the outside. There's an outside radius. So like I said, the outer radius, according to that figure, is all the way from the x-axis up to 1. We're spinning around the x-axis. So how far does this region go on the outside? The outside strip goes all the way up from the axis of rotation, from where y is 0, the axis of rotation, up to y where y is 1. So that entire height or radius when you spin around is going to be 1. So if you found that thing from 0 to 2, then you'd find the volume of the entire region spun around there, but that's too much. We want to take out the gap. Notice they just subtract off the integral of the gap. The gap is, well, how would you set this one up? It's, well, you got to find the height of this thing, which is the y value on the top minus the y value on the bottom. The y value at the top is just x squared minus 4, or excuse me, x squared divided by 4, minus the y value at the bottom, which is 0. So that's the height of this strip, and if you spin it around, that'll be the radius of this thing. So when you subtract off this inside volume, basically what you're going to do is you subtract off the integral. Integral is pi r squared, the radius of this thing when you spin around is the height of your strip, which is 1/4 x squared. That needs to be squared because it's r squared. And that would give you the area of this inside part times its thickness, which is again dx. And so this is the volume, this integral is the volume of the outside spun around, which is too much. You subtract off the volume of the inside because you don't want that gap in there. You don't want this little y region. And that's essentially what washers is. Washers is just, hey, I'm going to find, if there's a gap, I'm not going to worry about the gap. I'm going to integrate the whole thing with the gap included. I'm going to subtract off the gap when I'm done. So that leads us to the main equation for this. And I'll go back to that real quick because it's important. So essentially for discs or washers, notice that they're both kind of including the same thing. You don't have to do them separately. When you set up your integral, this slice, this disc you first set up is going to be whatever the outside radius is to your function, rotate around pi r squared. But you're subtracting off the inside spun around, this little tinier part. So you could do pi times the inner radius squared, subtract that right then. You don't have to do two separate integrals. You can take care of it in one integral. So what's the area of a washer, or the volume of a washer? Well, it's pi r squared, the outside radius. That'll give you the big circle's area, but you need to subtract off the little tiny piece that you don't want. You don't want that inside piece. So minus pi r squared, r is the inner one, and that will give you the area of the washer with the hole inside of it. And what's the volume of the washer then? Well, it's that area, pi r squared, big R, minus pi r squared, the little r, times its thickness, which is either dx or dy. So again, that's the concept. You want to keep the concept in mind when you're doing all these kind of things. All right, so back to examples. Let's say you had this thing. This is a good one. Let R be the region bounded by y equals 4 minus x squared. So you see that that's this parabola right here going down. And y equals 0. Y equals 0 is just the x-axis. So they're just saying this parabola and this x-axis. So it's just talking about this region in gray right here. This is the region we're going to take and spin around something. Find the volume of the solid obtained by revolving this region about the line x equals 3. So if you take a look at this thing, that's kind of cool what shape it makes. Kind of like a, I don't know, like a Jello mold or something like that when it's spun around, or some kind of bundt cake or something like that. But let's talk about how it would do this. Well, here's what we're going to do. Notice here's the line x equals 3. That's what I care about, my axis of rotation. I'm spinning this thing around x equals 3. How far out will this thing go? What's the strip to the outside, the farthest away from it? Well, it's this RO here, this outside radius right here, RO. And, well, it's the distance from the line of rotation to the function over here on the left. That's the farthest away it's going to go. That's what you want. Farthest one away from the axis is always going to be the outside radius. Well, let's see. What's the inside radius going to be? What are you going to take out? Because you notice that there's this gap right here. There's this gap right in here between 2 and 3. All this region here, you don't want that. You're not trying to spin that region around the axis. So we're going to take it out with our washers, which means we're going to subtract off the inner radius of this thing squared, you know, pi r squared. We'll do all that in a second. But as a concept, the outside radius is the distance from 3 to this x coordinate on the leftmost of the graph. The inside radius to the gap, it's always to the gap, is going to be the distance from 3 to the right side of this function right here. So let's see how we would set that up with an integral. So notice that this parabola is y equals 4 minus x squared. We probably want to solve for the x's because the radiuses are going to be distances along the x from x equals 3 to x to whatever the thing on the parabola is. So we're going to have to figure that out in terms of x's. So if y is 4 minus x squared, then you solve for x. X is either plus or minus the square root of 4 minus y squared. Or excuse me, X is plus or minus the square root of 4 minus y. Which one do you pick? Well, it depends. On this figure, on the left half of the plane, over on this side, x's are negative. So for this chunk, when I'm trying to find the outside radius, what are we going to use for x? X is negative over here. We're going to use for this chunk, x is negative square root of 4 minus y. However, for the inside radius, that inside radius is the distance from x equals 3 to the right side of this parabola. And on the right side of this parabola, x is positive, which means you're going to use x as 4 minus y for that. So what's the outside radius? Well, it's the length of the sliver right here, RO. And again, how do you find that? Well, it's the x on the right minus the x on the left, which in our case, for this side of the parabola would be 3x on the right minus the x on the left, which we just said since we're on the left side of the plane is the negative square root of 4 minus y, which cleans up to be 3 plus 4 minus y. That's the outside. Right there, outside radius to the outside of your washer. To the inside, to the little one, well, let's talk about the inside radius. It's the distance from x equals 3 to the right side of this parabola. So what is it? Well, it's x on the left minus x, x on the right minus x on the left. X on the right is again 3. The x on the left is the x coordinate of the right side of this parabola. Now, if you solve for x in terms of y, that one was the positive square root of 4 minus y. So the inside radius would be 3x on the left minus square root of 4 minus y, which is x on the left. Okay, that's the hard part. Find the equation for the outside radius, the inside radius, stuff like that. After this is really going to be easy. So what's the volume of this thing? Well, it's the volume of the outside circle, the entire thing spun around the axis, which is pi times the outside radius squared times the thickness. Notice, since the strips are going left and right, the thickness is dy, so everything's in terms of y. So the outside radius is pi times the quantity 3 plus square root of 4 minus y and quantity squared. That's the area of the outside part of the disk times its thickness dy would give you a little bit of volume. So this is the volume of the entire disk. Minus the inside part, the washer part, the part we don't want, that gap. Well, that's pi times the inside radius squared dy. And you just plug everything in, crank it all out, and you get 64 pi for the volume of that weird jello mold thing, which is kind of cool. So the last little bit of advice for you guys is, this is kind of tricky, and I know I'm not there to help you guys with the geometry because setting these up is tricky, but that's why I'm really trying to hit, what's the length of a strip? It's if it's a vertical one, it's the y on the top minus the y on the bottom. What's the horizontal strip? It's the x on the right minus the x on the left. The reason I'm trying to keep emphasizing this is because it works between two functions or between a function and a random axis you're spinning around. You need to think about what these strips are in terms of just distances and y's, distances and x's, because those are what's going to represent radiuses in this one when you spin it around either way. It's going to help later on in the next section when we do shells, which is an alternate way to find volumes. So really just think about, okay, what's this little chunk of volume? Well, in general, for a washer, let's say, it's going to be pi times the outside radius squared minus the inside radius squared, because that's going to give me the area of the washer times its thickness, dx or dy, or whatever I happen to be doing. That'll give me the volume of the washer. And then I just integrate them all up from wherever to wherever. Integration is really easy. You should be spending 90% of your time setting these up and carefully thinking about what the radius is and all that junk. Okay, so here's your homework one more time. Now, I am going to always model one of them for you. I'm not going to do it on the whiteboard anymore. I learned my lesson from the last lesson, so we're going to walk it through a little piece at a time. So the one I'm going to model from your homework is number 22. I'm just picking a random one, kind of close to the end, because I figured those would be difficult for you. And number 22 says, region bounded by y equals secant x, y equals 0, x equals -1 pi over 4, and x equals positive pi over 4. And there's two different parts of this, A and B. Part A is what happens if you took this region and revolved around y equals 2, and second part, what if you revolved around the x-axis? Well, okay, let's get our bearings first. You always want to know what they're talking about, what the region is. So The blue line is secant x, if you graph it and kind of zoom in. Y equals 0. What they're telling you there is y equals 0 is the x-axis. So that red line there represents the x-axis, but you got to remember it's between secant x on top and y equals 0, the x-axis on bottom. They also say x goes from negative pi over 4, that's the green line, all the way over to x equals pi over 4, which is the purplish line. So you see this gray area shaded in here, that's the region they're talking about. So I need to take this region and part A spin around the line y equals 2, and for part B, we're going to spin around the x-axis. So let's see how we would go about doing that. Okay, for part A, you're spinning along the line, about the line y equals 2. Now, y equals 2, if you think of that graph, that's the orange line right there. If you're spinning this around, this region around y equals 2, notice there's a gap you're spinning around too, which is why you would not use discs, but you use washers. If there's ever a gap you're spinning around, you need to use washers too. Okay, well, how are we going to do this? Well, we're going to take a little slice at a time. We're going to take a certain height. We're going to take a rectangle, still rectangles. We're going to spin it around. And I'm going to use from now on, I'm going to use capital letter R for the big radius, the outside one. I'm going to use lowercase r for the little radius. So sometimes I'll just say R outer and R inner. Sometimes I'll say just big R and little r, just so you know those two are kind of equivalent. I use big R and little r myself, but use whatever that you want. So again, let's see what we're going to do. We're spinning this around the line y equals 2. So if we're going to go around the line y equals 2, what we're going to do is we're going to draw a strip for the outside radius. So it's always to the outmost part, the farthest part of your region. So let's see. Where's the distance from my axis of rotation to the most outside part of my region? Well, my axis of rotation is y equals 2. So up here where y is 2. And way down, the strip is going all the way down to the x-axis, because the region, the gray region, always goes down to the x-axis. Well, in this case, no matter where you draw your strip, the height of this thing is going to be the y on the top, which is 2, minus the y on the bottom, which is 0. So the height of this strip is going to be just 2 minus 0, or 2. So remember, we're taking this strip and we're spinning it around the line y equals 2. So my outside radius, big R, will just be 2. Of course, that's too much because that spins everything below y equals 2 and the x-axis around. We need to take out the gap. Well, that's why you have the minus r pi r squared, the little r. Well, what's this little radius? It's the distance from y equals 2 down to this y value. Well, that y value is on the blue curve, which was secant x. So the length, excuse me, the height of this entire little radius, little r, is 2 minus the y value, which is 2 minus secant x. Now, how thick are these little tiny circles we're going to spin around these washers? Well, since the strips are going up and down, the thickness is going to be dx. So let's set up conceptually what a little chunk of volume is for this washer. The washer is going to be, well, pi r squared, but the r squareds are subtracted because you have the area of the outside, pi big R squared, minus the area of the inside, which is pi little r squared. So that's the thing of the washer with the hole. So this pi times the quantity big R squared minus little r squared n quantity, that represents the area of your washer. Of course, the washer is dx thick, so area times thickness is volume. So dV is going to be pi big R squared minus little r squared times dx, the area of the washer times the thickness. And plugging things in, the big R was 2 minus 0, the little r was 2 minus secant. You plug them all in, you do a little algebra and clean up, you get that the little chunk of volume is pi times the quantity 4 secant x minus secant squared x when you get all done with it. Okay, well, we're pretty much done. That's the hard part. You know, we got dV. I know the rest looks horrendous, but it's just tedious, you know, algebra and basic integration. So essentially, what are we going to do? We got the equation for one of the washer's volumes. So we're going to add up all these washers from, well, we're doing dx. So where's x begin and end? According to the bounds, x starts at negative pi over 4 to positive pi over 4. So that's my limits of integration. You add up all the little volumes, you get the total volume. And you carefully do your integrals and plug in things.
check the back of the book on these. A lot of the back of the books might give you decimal answers because they might just, guys, honestly, I'm 90% happy if you just set the volume integral. If you want to let your calculator do a lot of the work, like for example, right at this step right here where I say volume is this integral, if you want to let your calculator go do it and avoid all this ugly work and gain an exact answer out, I guess I'll let that fly. I'm far more concerned with you guys conceptually setting up the first, say, 3 lines of this work right here. I know what DV is as an idea is. I know how to set up what the strips, what the radiuses are going to be. I understand what the limits of integration are going to be. That's the tricky part. So if you get that, I'm not so much going to make you go through a bunch of tedious, okay, what's the secant of pi over 4, and do I need an absolute value, and can I use properties of logs and condense them, and can I rationalize it? There's a lot of algebra in here that is just making it prettier and an exact answer, but I really want you guys to get the correct answer. I'm not so concerned with it being exact. Maybe a decimal might even be okay on these. So you want to just set the integral, and in fact, for grading purposes, since we're doing this long distance, I might actually just want you to do that. Just maybe get to the point where you set the integral. I want to see v equals integral blah, 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 blah. And if you just want to plug that stuff in your calculator and let your calculator figure out the decimal value is for that, I'm okay with that. But if it's really simple, if you're doing like the integral of x, please don't, from -1/3 to 1/3 or something like that. You should be able to do that. You should be able to give me an exact answer. So don't, use your best judgment. Don't be sloppy. Don't cheat too much. Okay, so there's the first one. And that's with washers when it's around y = 2. That was actually the hard one. For part B, what they're going to do is they're going to take this function, this region, actually, and they're going to spin around not y = 2, but y = 0, i.e. the x-axis. Now, in this case, it's going to be a lot easier. You don't have a gap that you're spinning around. You're just taking this region, which is bounded by secant x and the x-axis, and you're spinning around the x-axis. So there's nothing to take out. Disks is fine. You can think of disks as a special case of washers. Washers, what's a disk in terms of a washer? Well, a disk is a washer where the inside radius is just 0. You're not taking out anything. So it's just pi r squared, basically. So I'm going to use little letter r. Again, big R, little r, doesn't matter, just the concept. It's the exact same idea, though. So what am I going to do? I'm going to take this little strip right here. This is the height. It's the y value on the top minus the y value on the bottom is the height. The y value on the top is secant. The y value on the bottom is 0. So secant minus 0 is just secant. That's the height of this. The height of this strip represents the radius because you're spinning it around the x-axis here. So the radius is from whatever the x-axis is up to the function, which is the height of the strip. So pi r squared is going to be pi times secant squared. Well, that's great. It makes a little circle when you spin it around. What's the thickness of that circle is dx. So the little volume of this disk that you've spun around, this circle, so I shouldn't say circle anymore, I should say disk. The volume of this disk is whatever the areas of the disk is times the thickness of the disk. So the area is pi secant squared x, and then you need to times it by dx, and you're done. That's an error right there on this slide. I should have pi secant squared x dx. I'm missing the dx, so, whoops. Put the dx in there. But that's it. You got the dv set up. It's really easy after that. Now you just got to add up all the volumes of all these disks. So you're going to, again, integrate it from whatever the x, this is dx stuff, so x goes from -pi/2 to pi/4. Integral of secant squared is tan. Now that's pretty easy. This is one of those ones you should be able to plug in and get me an exact answer because tan of pi/4 is 1 and tan of -pi/4 is -1. Put all in, and the volume of this thing is 2 pi. So it's going to take a little bit of practice. Look at the examples in the book. Look at these examples right here. We're going to start having office hours as of today. Now, I don't think many people are going to attend, but if you want to, you're welcome to. For questions, today's the 25th. I'm trying to have them on Wednesdays and Fridays at 2:00 p.m. So if you can make those, great. If not, just contact me sometime. But that's when I'd like to do most of our work because we can talk one-on-one. I can see what you're doing. I can point out real quick, okay, that's wrong, that's wrong. It's a lot easier than emails or text or anything like that. So try to make them if you can. Technically, school isn't starting for a while yet, but like I've been saying, stay on task and more's coming. So there you go. Good luck with your slices. Remember, pi r squared times thickness. R is whatever the length of your stupid strip is or height of it is, and from the axis of rotation to your function, and your thickness is dx or dy or whatever. And if you have a gap, subtract off the inner radius too. So slicing discs and washers, you might want to watch it a couple times to get the gist of it. This is kind of a jump. I remember this kids really struggle with setting these up. So again, show me you can set them up. Show me your integral, and if you want to let your calculator do the rest for moderately difficult ones, you're welcome to. Okay, that's it for that, guys. I'll talk to you soon, and have a great day.